Good day, I'm Kelvin Sattler, and today I'll be discussing my research program at the Ripley Landslide. There are two parts to this study. First, the development of a low-cost data logger, and second, their use in a large monitoring network studying variable water content and its impact on landslide displacement rates. An initial secondary objective of this study focused on the development of a low-cost version of a standard data logger to help expand basic commercial monitoring networks at a quarter of the cost. Primary focus was to study the long-term variations in soil water content and relate these changes to displacement of the Ripley landslide. The present study analyzes the viability of water content, electrical resistivity tomography, and matrix suction as early warning indicators of slope displacement rate changes. The study of variable soil water content adds a missing link to the overall study of the Ripley landslide. The custom data loggers were developed with a few goals in mind. Commercial data loggers can be very expensive given their capabilities. This data logger was constructed at 4 times less expense than commercial units with similar capabilities. The data logger materials used low-cost components with open-source literature. The code I have developed is available as an open-source resource on the U of A repository. The data logger was designed aiming for commercial-grade reliability and durability in field application. As a benefit to their lower cost, instrumentation engineers can get more data for their dollar. Another goal was to reduce peripheral components and proprietary knowledge that add cost and complexity to the data collection process. Finally, it was important to develop a data logger that was adaptable to a variety of sensors. Geotechnical practitioners and researchers can agree that it is often important to keep things simple. Prior to starting on this project, I had no knowledge of how to code or work with any of these components. The data logger development required a few months, but I was able to send the components to Dr. Haji Abdulrazak at the U of A and instruct her how to set it up through a Skype call. A variety of open source hardware and attachments were used to simplify the setup, including the Arduino computer microcontroller, which is the brains behind the data logger. The Arduino project began 15 years ago and focuses on providing a low-cost learning environment typically used by students to interact with various sensors and circuits. The Arduino microcontroller has gained a significant following for its versatility, widely available hardware, attachments, open source libraries, and online support forums. As a result, the entire system is highly adaptable to a variety of sensor types. SDI-12 sensors come in various forms and are commonly used in environmental monitoring. I tested 2 types of environmental sensors, volumetric water content and matrix suction sensors. Online open source libraries provide example code that have been extensively tested for a variety of sensors. With the use of example codes, I assembled my own code for the low-cost data logger. The algorithms in the code unpack the SDI-12 sensor's output to convert the signals to recognizable measurements. A primary benefit of SDI-12 sensors is that they only require 3 cables. 2 of these cables are used for power, and the remaining cable transmits data for all sensors. Sensor addressing enables the code to unpack data and assign measurements to each individual sensor. Data verification was completed in the lab, and SDI-12 sensors are currently being measured by low-cost data logging units in all 3 Western Canadian provinces. The plots on the right demonstrate the data logger's continuous function throughout this past winter at CP Scotford Subdivision Mile 153.8 northeast of Edmonton, and the Borden Bridge north of Saskatoon. At the Ripley Landslide, matrix suction sensors on low-cost data loggers have been installed as well as suction sensors on commercial units. While the sensors are approximately 50 meters apart, they are both installed within the headscarp of the landslide. After initial equilibration during the first 2 weeks, measurements indicated similar trends in both the matrix suction and the soil temperature. Absolute values are also similar, especially at greater depth. At shallow depth, differences in matrix suction are to be expected, because vegetation is not consistent from one borehole to the other. The commercial logger is also more sheltered at the surface due to the width of the tension cracks at this location. However, this demonstrates that measurements do not vary greatly based on the data logger type and validates the supplementary use of these low-cost data loggers. The data logging unit was installed at 3 field sites in BC, Alberta, and Saskatchewan, with a future site planned at the Assiniboine River Valley in Manitoba. The loggers were designed around a hard shell carrying case with a customizable pull-away foam interior and mounting brackets for standard 2-inch post installation. Cable armoring was found to be a requirement in remote areas where wildlife pose a threat to loose cables. Data acquisition simply involves removing a standard SD camera card, downloading the data, and replacing the SD card. Data loggers are only reset to refresh the real-time clock as they drift, which is also a common problem in commercial loggers. No programs need to be downloaded before traveling to the field site. The only requirement is an SD card reader, which comes standard on many laptops, or at least is commonly available in many stores. Field application over the past 3 years has demonstrated that temperatures do not present a major problem. The main concern, however, is solar power needed to recharge the batteries. Number of hours of direct sunlight play a major role in recharging capabilities. Steep slopes intersecting the horizon from the data logger's perspective cause most of the issues. Proximity to the slope is also an important factor. Data loggers closer to the base of the valley perform much better than loggers on the valley side slope. In the left image from the Ripley slide, the 2 loggers in the foreground consistently record data further into the winter than the logger circled in red. The circled logger receives limited direct sunlight in the winter as it is pushed back into the northwest facing slope. In the right image from the Borden Bridge in Saskatchewan, the logger shown in the foreground had some issues with winter sunlight. However, 2 loggers in the background, indicated by the green arrow, functioned throughout the winter with no issues. At CP mile 153.8 in Alberta, the topography is relatively flat and lack of solar power has yet to be an issue. Therefore, loggers installed on north-facing slopes are the only locations where performance may be an issue. South-facing slopes would actually be beneficial, although flat surfaces with few obstructions also have no problems in winter months. The current setup I have been using records data every 20 to 30 minutes. However, this could be scaled back considerably to conserve power for many geotechnical applications. The development of a low-cost data logger for matrix suction and soil water content led to the publication of open source code, allowing other researchers to start installing these data acquisition systems at several study sites. Laboratory tests were also completed to analyze signals from vibrating wire piezometer sensors, or VWPs. These have been tested in the field, but to a lesser extent. As previously mentioned, one such use of these data loggers was at the Ripley Landslide, which is one of several translational, slow-moving landslides in the Thompson River Valley south of Ashcroft, British Columbia. A major factor in its stability is the seasonal changes in river level, which can vary by 8 meters throughout the year. The base of the Ripley Landslide is directly exposed in the Thompson River, and potential triggers for displacement include the buttressing effect and drawdown effects caused by changing river elevation, artesian pressures underneath the landslide toe due to regional groundwater flow into the Thompson River, erosion exposing geologic controls, and irrigation on the upper terraces. The present research is focused on variable soil water content in the unsaturated vadose zone near the headscarp. Due to the steep terrain in the valley and the deep water table, a significant component of the landslide's mass is unsaturated, and stability from this part of the landslide should not be neglected. A detailed network of instruments has been installed, including permanent and mobile GPS stations, corner reflectors for satellite-based interferometry, geocubes, piezometers, and shape acceleray or SAA inclinometers. More recently, a weather station was installed and became operational in September 2016. In December 2017, installation was completed for a permanent layout of electrical resistivity tomography, or ERT, and the British Geological Survey began taking regular readings. Between 2017 and 2018, 5 sets of matrix suction sensors, with 2 commercial and 3 low-cost loggers, were placed at several locations along the headscarp. Particular attention is focused on the 2 suction boreholes near the center of the Ripley slide, entitled Slide Mass Suction and Headscarp Suction. These matrix suction sensors were originally developed for the agricultural irrigation industry. The manufacturer claims plus-minus 10% accuracy for soil suction measurements between -9 and -100 kPa that may extend down to -2000 kPa for some soils. The linear interpolation extends down to a minimum reading of -100,000 kPa, which is reserved for air-dry soil conditions. They operate based on the premise of water potential equilibrium between the porous ceramic disc and the soil medium. The relative permittivity of the ceramic material is measured and is directly correlated to the ceramic's water content. The soil water characteristic curve for the ceramic disc is well defined, allowing us to calculate the matrix suction of the porous stone. Provided that the sensor is placed in good contact with the soil in the borehole, we can assume that the water potential equilibrium exists between the two, giving us the soil suction. Over a 3-year span, matrix suction measurements have been collected at Ripley. The 2 records of suction shown here are from the 2 suction boreholes mentioned previously. These boreholes are only 4.5 meters apart, but one is installed in a tension crack in the headscarp and the other in the slide mass. The relative differences in seasonal variations of matrix suction are immediately apparent. In the bottom plot, the slide mass suction changes seasonally, while in the top plot, suction in the headscarp tension crack demonstrated a lower and more consistent level of matrix suction. The lower level of suction, closer to saturation, also implies a higher hydraulic conductivity. As a result, a higher rate of infiltration can be expected throughout the year in the tension cracks. While the ERT transects across the Ripley Landslide do not measure soil water content or matrix suction directly, they do provide visual clues to changes in soil water content that are occurring. The system was installed as part of a collaborative effort between the Geological Survey of Canada, U of A, U of S, and the British Geological Survey. Variable soil electrical resistivity is attributed to changes in the soil water content. Water-filled pore spaces have low electrical resistivity, while air-filled pore spaces have high resistivity. The British Geological Survey is currently working on calibrating soil electrical resistivity to soil water content. In the meantime, subsequent surveys of electrical resistivity provide valuable information about the areal extent and depth of infiltration across the ERT transects. Visual plots such as these have been reproduced on a weekly basis since December 2017. Increasing water content, or negative changes in resistivity, are depicted in blue on the following plots. Wildlife cameras show the surface conditions and accumulated snow present at the time of each ERT measurement. Air temperature across the survey period is shown at the bottom. The following plots show spring ground thaw and snow melt in early 2018, leading to infiltration within the headscarp tension cracks. The infiltration is evidenced in part E of the figure, where a dark blue crescent extends downwards in the location of the headscarp. The tension cracks act as a collection basin for blowing snow in the winter and overland runoff in the spring. When temperatures rise above melting, accumulated snow releases water directly into the tension cracks. Therefore, a major component of the vadose zone water content appears to have been derived from tension crack infiltration. Matrix suction measurements and ERT plots demonstrate that soil water content follows specific seasonal patterns that can vary from year to year. However, it requires a fair bit of effort to develop matrix suction monitoring networks or to install an ERT array. Therefore, I decided to also develop a monthly indicator for soil water content using standard meteorological data in the form of a soil moisture deficit, or SMD, calculation. Soil moisture deficit was determined from an estimated evapotranspiration based on Penman-Monteith and ASCE methods, while the site's precipitation was measured at the weather station. By plotting a time series of soil moisture deficit, it was possible to determine which years were wet or dry when compared over several years. From the plot shown here, soil moisture deficit provides a reasonable representation of the matrix suction variation in the slide mass on a multi-year scale. When soil moisture deficit reached a maximum during summer, the near-surface matrix suction peaked at a seasonal maximum. A slight delay is observed between the soil moisture deficit changes and the associated suction response with depth due to infiltration rate, unsaturated hydraulic conductivity, and soil depth above individual sensors. From the plot, we can infer from soil moisture deficit that 2018 had a slightly drier summer compared to 2019 and 2020. The same trend was observed for the solid line indicating slide mass suction at 0.9 meters below ground, denoting higher soil water content in 2019 and 2020. This demonstrates that wet years, marked by a lower suction, correspond to wet years marked by lower soil moisture deficit. Therefore, meteorological data used in the soil moisture deficit calculation provided a reasonable approximation for near-surface soil water content. The soil moisture deficit was calculated over a 5-year span and compared to the measured SAA displacement and Thompson River level. The goal was to determine whether near-surface soil water content has an impact on displacement rates that was not being accounted for by only analyzing the changes in river stage. An increased displacement rate event for the Ripley Landslide occurred in February 2017, following a particularly wet year in 2016. While the seasonal maximum and seasonal minimum river levels were approximately identical between 2015-16 and 2016-17, the movement did not occur until 2017. In effect, the displacement event followed the wetter year, as described by the 2016 soil moisture deficit, with a much lower peak value. Furthermore, the seasonal minimum river level in 2016 and 2017 were higher compared to other years, so there was no unusually low river level in 2017 that one could attribute the displacement to. The buttressing effect from the relatively high seasonal minimum river elevation in winter 2017 would have benefited, not hindered, stability when compared to lower seasonal minimum river levels that occur in other years. While seasonal changes in river level have an important impact on seasonal changes in displacement rate, as shown by the flattening of the displacement during high river levels, they do not always tell the whole displacement story from one year to the next. Multi-year trends in soil water content due to antecedent precipitation and other meteorological factors, summarized as a soil moisture deficit, have a role in year-to-year displacement rates. These trends can be combined with the analysis of changing river levels to provide early warning for years with abnormally high displacement rates. The final aspect of this study was to quantify the impact of these near-surface soil water content variations on the overall stability. I began the modeling with a simplified 2D analysis at 3 cross-sections across the Ripley Landslide in the software program GeoStudio. A fully specified slip surface was applied and displaced translationally along a known residual strength slip plane around 257 meters above sea level. All scenarios involved the Thompson River level at the seasonal minimum, around 263 meters above sea level, and a land-climate interaction boundary along the ground surface. Geotechnical properties for the various stratigraphic layers came from the previous studies of Ashragian and Hendry. Focus was placed on the unsaturated strength contribution from the diamiction till unit 6 found in the upper reaches of the landslide. All other units were assumed to have no unsaturated strength component because they were composed of coarse-grained material, were non-existent in the cross-sections, or were present well below the ground surface, and conditions there were expected to remain saturated. An important component of determining the strength to be gained from unsaturated soil is the soil water characteristic curve, or the SWCC. The SWCC describes the relationship between the soil water content and the soil suction, demonstrating that increasing soil water content reduces the matrix suction, thereby reducing the soil's shear strength. Soil samples were collected when the matrix suction sensors were installed, and tempi cell tests were used to determine the SWCC relationship. The following drying curve was measured for soil samples collected between 1.2 and 1.5 meters below ground within the slide mass. The plot demonstrates that small changes in soil water content cause changes in matrix suction of several orders in magnitude. Therefore, it is shown that monitoring the soil water content, or the matrix suction, provides an important variable in the study of displacement rates at the Ripley Landslide. I tested two scenarios of transient seepage for all cross-sections using the previous back-analyzed geotechnical parameters. The first involved the rapid melt of a 0.3 meter snowpack using an observed rise in temperature from January 3rd to January 15th, 2020. The second analyzed a 25 millimeter precipitation event that occurred over a 15-day period from January 31st to February 14th, 2020. All meteorological data used in the analysis was measured at the on-site weather station. Stability analysis was calculated at quarter-day increments over each period to document the change in factor of safety. Both scenarios indicated potential changes of up to 10% in the overall factor in safety. On the other hand, the seasonal variation in the river stage accounts for about a 20% change in factor of safety. Therefore, near-surface soil water content variations can have potentially large impacts on slope stability, especially if these scenarios coincide with the seasonal minimum river level. Future work on this study will involve calibrating these models to the measured matrix suction from the various boreholes and soil water contents inferred from the ERT transects. I am also working towards developing a 3D model of the Ripley landslide using several years' worth of borehole data, and hopefully soon the recently completed September borehole investigation data from BGC Engineering. So I'd like to thank my supervisors, David Elwood from the University of Saskatchewan and Michael Hendry from the University of Alberta. I'd also like to acknowledge support from the Geological Survey of Canada, the British Geological Survey, Clifton, Transport Canada, and both CP and CN through the Canadian Rail Research Laboratory. Thank you, and now I'd like to open it up for questions.